The next example, for part A, we can use the ideal gas law to find the volume at point A to be given by nRTH over the pressure at point A. We're given that we have 0.2 moles. The gas constant is 8.314 joule per mole Kelvin, and the temperature is 227 plus 273.15 kelvins over 10 times 10 to the 5th pascals, which gives us a volume of 8.31 times 10 to the minus 4 meters cubed. And in process A to B, we know that volume at B is twice the volume at A, so that's going to be 16.62 times 10 to the negative 4 meters cubed. And we have, for an isothermal process, we have the pressure at one point times the volume at one point is constant, so we can use VA times PA equals VB times PB, which means the pressure at point B is going to equal VA over VB times PA. And since VA over VB is 1/2, this is going to be 1/2 times 10.0 10 to the 5th Pascal, or 5.0 10 to the 5th Pascal. For the process BC, it's an adiabatic expansion. We know that for an adiabatic expansion, that the temperature times the volume raised to the ratio of heat capacities is constant. So the following is true, and we can find that the volume at point C is going to be VB times temperature at the high point over the temperature on the low point raised to 1 over the ratio -1, which is the same as minus that ratio. So this is going to equal 16.6 times 10 to the minus 4 meters cubed times the quantity 500 K over 350 K, all raised to the 2.5, and that gives us a volume of 59.6 times 10 to the negative 4 meters cubed. And using the ideal gas law, then the pressure at point C is nRT over V, which is 0.2 moles times the gas constant times the temperature point C, which is 300 kelvins, all over the volume at C, which we just found. And that gives us a pressure of 0.837 times 10 to the 5th Pascal. And for the adiabatic process now from D back to A, we can use that V at D, as we did before, is V at A times TH over T sub C to the 1 minus eta minus 1, nu minus 1, which is 8.31 times 10 to the negative 4 meters cubed times 500K over 350K raised to the 2.5, which gives us a volume of 29.8 times 10 to the minus 4 meters cubed, and then the pressure at point D is going to be nRT over BD. Since it's constant between C and D, the temperature at D would be the same as temperature at C, which equals 0.2 moles, 8.314 joule per mole Kelvin, times the temperature at C, which is 300 kelvins, over 29.8 times 10 to the minus 4 meters cubed, which will give us 1.67 times 10 to the 5th Pascal. For part B, if we look at the process from A to B, it's isothermal. And that means that the change in internal energy is 0. We know that the work for AB then is going to equal the heat for the process at AB, and that's going to equal nRT times the natural log of V at B over V at A. Plugging in, we get 0.2 moles, 8.314 joule per mole Kelvin, times the heat at the high reservoir, which is 500, times the natural log of the volume B over volume A is 2, because VB is 2 times VA, and this gives us 576 joules. Now for the process from B to C, it's an adiabatic expansion. That implies that the heat is 0. That means that the change in internal energy from B to C is going to equal minus the work from B to C. And the work from B to C is going to equal minus the negative change in internal energy, which can be given by NCV T cold minus T hot, or T low minus T high, which is the same as saying NCV TH minus T sub C. If we take this minus sign and distribute it in there and plug it in the numbers, now we get 0.2 moles times CV, which is given as 20.8 mole joule per mole Kelvin, times the change in temperatures, which is 500 K minus 350 K, and that gives us a work of 832 joules. Next process we have is from C to D. It's isothermal. So again, that means that the change in internal temperature from C to D is 0, which means also that the work from C to D is equal to the heat from C to D, and that is equal to the heat at C, which is nRTC natural log of VC over VD over VC. And plugging in, we get 0.2 mole times 8.314 joule per mole Kelvin. Temperature at C is 300 kelvins. Natural log of 29.8 times 10 to the negative 4 meters cubed over 59.6 times 10 to the negative 4 meters cubed, which gives us a value of negative 346 joules. And lastly, for part B, we have the process from D to A, which is an adiabatic compression. So that means that the heat is 0, and the work for the process from D to A is negative the change in internal energy from D to A, which is minus NCV TH minus TC, which is the same as NCV TC minus TH. And plugging in our values, we get 0.2 moles CV, which is 20.8 joule per mole Kelvin, times the change in temperatures from C, which is 300 Kelvin, to 500 Kelvin, or negative 832 joules. For part C, we're asked for the efficiency directly from the results from part B. So we can say the efficiency equals the work over the heat at the high reservoir. And So we can say this is, if we add all the works, we get 576 joules plus 832 joules minus 346 joules minus 832 joules over the heat at the high reservoir, which is 576 joules. So this gives us an efficiency of 0.4 or 40%. And we can also have done this by saying that the efficiency is the difference between the two reservoirs over the high reservoir temperatures. So this is 500K minus 300K over 500K, which is again 0.4 or 40%. For part D, it's asking us if we rerun this cycle backwards, what is the coefficient of performance for the refrigerator. So we can say that if this is run backwards, the numbers will not change, the values, or whether it's coming in or leaving will change. So the Q at C is negative 346 joules, and the work done is going to be 230 joules, and the coefficient of performance, capital K, is the absolute value of QC over K over W. So this is 346 joules over 230 joules, which is, if we round to significant figures, 1.5. Because this is a Carnot engine, we could have also done that the K is TC over TH minus TC, which is 300K over 500K minus 300K, which is also 1.5. So one way or another you get the same answer. E, it's asking for the change in entropy during one cycle, and the change in entropy is given by the heat over the temperature at the high reservoir. So that is 2000 joules over 500 Ks, which is 4.0 joule per Kelvin. And for the low reservoir, delta SC is QC over TC, which is negative 1400 joules over 300 K, which is 350 K, sorry, which is negative 4.0 joule per Kelvin. So the total change in entropy, delta S, is going to be delta SH plus delta H SC, and we see that that is 0. In fact, anytime we do a complete cycle, the change in entropy should be 0 at the end.